Hello, my name is Zheng Gu. I am a graduate student here at the University of California, Berkeley in the Department of Electrical Engineering and Computer Sciences. And I am working under Professor Jeffrey Boker in Theme 4 of the Center for Energy Efficient Electronics Science. And today I am here to talk to you about spin logic. And so in this lecture, I will present to you an overview of spin logic and spin logic research. And let's begin with the fundamental motivation for developing spin logic. In traditional electronics, performing digital logic requires having two logical levels. We call them 0 or 1 or true and false. And we essentially move charge, electrons, between these two voltages. And that requires thermodynamically an energy of N, which is the number of charges, times the thermodynamic energy, and the log of R, where 1 over R is the rate of errors. Now, let's come over here and look at spin logic. Fundamentally, instead of moving this charge, we can just take electrons which have intrinsic spins and we just flip the spin. And if we have simply n spins, then again we would have n times kT ln R. However, if our ensemble of spins is strongly coupled to each other, say via the exchange interaction, as would happen in a regular ferromagnet, then they would reinforce each other so that they all point along the same direction. And in that case, it would become more like a single giant spin. And in that case, the energy, because there are only two now possible states, just all spin up or all spin down, it would reduce to just 1 times kT ln R. And this is a very big difference. N is typically these days in the thousands and tens of thousands. So we're talking about multiple orders of magnitude in energy dissipation difference. In addition, moving charge leads to ohmic dissipation or resistive heating, what's called Joule heating. And here, in spin logic, we do not have to move any charge at all. Also, moving a charge between two voltage levels is essentially charging and discharging a capacitor. And there is leakage in charging and discharging a capacitor. But here, the spins in a ferromagnet retain their state. And that's called non-volatility. And that allows you to retain information for much longer times without having to apply more energy to refresh the system. So, I will go through a number of proposed spin logic systems that have been the topic of research interest in the past. The primary one of the main ones that we're working on in Theme 4 is called nanomagnetic logic, or NML. And the idea is we just have, as I've said before, an ensemble of n spins, but they're in this magnetic chunk or island, and the green arrows around it represent the magnetic field emitted by this island. This field is usually called the stray field or the dipole field, and that is if you assume that this island is a perfect dipole. Now, there's something called the Zeeman interaction, where if I put another magnet next to it, like for example here, then it is lower energy for the system to have the second magnet point along the direction of the field. And so that means this particular configuration is the lowest energy configuration. And if I put them end to end like this is also a low energy configuration. And so if I chain together these two magnets, notice that one is pointing up and one is pointing down. If we just make our logic levels spin up and spin down, then what this is an inverter, because we put in true or false, and on the second magnet we get the opposite. And then if I just stick another, say here, and go left to right or right to left, then this becomes a buffer. A buffer is just two inverters. And so we have a very basic structure here. We can have inverters and buffers, and then of course you can chain together multiple buffers, and that's essentially an interconnect. Now what about another basic logic structure? We need a gate, and so in NML we have what's called a majority logic gate. It's called that because the output magnet number 4 takes the whatever state is the majority of these three magnets inputs 1, 2, and 3, and there always is a majority because there's an odd number of inputs. And if you could just go through the dipole fields and figure out which configuration, let's say you fix the inputs 1, 2, and 3, you figure out, according to the Zeeman interaction, what the preferred state of the output number 4 is, and you make a truth table on the right here. And notice that if I just fix one of the inputs, say input 1, I can divide this table up into 2 sections, and each of these smaller sections is actually an AND or OR gate. And we know that if we have an AND or OR gate and the ability to invert, that is, have the NOT gate, then we can have a complete Boolean logic solution. So here's another version of NML. This is called perpendicular NML, and that's because the orientation of these magnets are pointing out of the slide. Now, the way that this works is this is also a majority logic gate. It has also 1, 2, and 3 inputs and an output. But where this red dot is, it's engineered to essentially switch at lower fields than the other magnets. And so this essentially adds directionality to the system. This means that instead of the output switching the inputs, it's always the other way around, because the output will switch before the inputs. Again, we have the same truth table, but now we apply this external field. And at some point, this field will be high enough so that only the output, magnet number 4, starts to switch. And again, the inputs will not switch because they have higher coercivity. And if we follow the process, then what happens is you keep this field applied, and this small domain that nucleates at the red point starts spreading, and it keeps going. So now this domain has spread throughout the entire magnet, and so we say that this magnet, the output, has now switched. And so you can see right away that the interconnect action here is actually within one solid piece of magnet. It's just this domain wall moving that gives you an interconnect. So in this particular architecture, you don't have to have a sequence of buffers and inverters. Now let's move on to a different kind of spin logic. So in these kinds of spin logic, we introduce some elements of charge logic. That is, we in some way use applied voltages and currents in combination with ferromagnets. So here is one that has been recently proposed. It's just called the spin switch. And here at Theme 4, we are also taking an interest in this particular architecture. And this one looks complicated, but it is essentially a replacement for the transistor, the field effect transistor. And let me go through with you how that works. So we have an input side, the left side, and an output side. Or we can call it a writing side and a reading side. And on the output side, what we have is essentially a source and drain. It's two constant voltages. One is positive and the other is negative. And then we have this structure, this stack. So this is called a magnetic tunnel junction, and the electrical resistance of this stack depends on how the ferromagnets that are in green are actually oriented. So if they are parallel, like here, pointing into the page, then the resistance is smaller. And if they're anti-parallel, like here, the resistance is larger. And so that means this output voltage here actually gets pulled up to plus Vs in this case. And then if I flip it, it gets pulled to minus Vs. And so right away I have essentially a voltage switch that can be controlled by this magnet. Now how do I switch this magnet? Well, on the other side, if I can switch the magnet on the left, and I can engineer my structure so that there's enough magnetic field coupling or otherwise some kind of magnetic coupling between the large magnet on the left and the large magnet on the right, so that when the left magnet switches, the magnet on the right also switches. That's what we need. That way we can control the right side, the output side, from the input side without actually having them interact electrically. There's this insulator here so that there's no charge flowing between the two. And then we flow a current through this blue material. It's a spin Hall effect metal, and that essentially what it does is it converts this charge current into some spin current. So I flow it through this material, and it actually applies some spin torque that allows it to switch the ferromagnet. If I rearrange this and I put minus Vs on this side and positive Vs on this side, then switching that polarity essentially is like switching between the NMOS and the PMOS transistors. That means that the same orientation of the ferromagnet on the right will lead to the opposite voltage VL. Here is something called all-spin logic. It is somewhat similar to the spin switch, but it allows for a longer range magnetic interaction through this material called a spin channel or a coherent spin interconnect. That just means if I inject spins into it from the left side, or whichever side, then that spin polarization will remain in the channel and eventually make it over to the other side. And if I apply a voltage, say between V1 and ground, then depending on the polarity of that voltage, I'll get a different polarity of the spin polarization in this channel. And then that spin polarization will apply a spin torque onto the second magnet and switch it. And so by applying this voltage pulse, I can switch another magnet at long range. And these segments here are separated by insulators. So this is, say, one stage. We have another stage and then a third stage. And because of this insulator, this blocks charge current as well as spin current. And so they don't interact in any way. And so if I apply the voltage here at V1, I know that it's only going to affect this magnet number 2 here. And then of course I can apply the voltage at V2 and I'll go on to the next stage. But I can also have multiple magnets where V1 is. If we imagine a top-down view, we can have several magnets here, and then they're connected by some of these spin coherent interconnects, and they go into, say, one output magnet. And you can actually, again, make a majority logic gate this way. Speaking of majority logic gates, here is another structure that's supposed to integrate with charge logic. And this is just the majority logic gate itself interfacing with the outside world only in terms of voltages. So we have, again, 3 inputs, 1, 2, and 3, and an output, and it follows a truth table similar to the other majority logic gates. This is called spin torque majority logic gate. The way this works is I apply voltages or currents on the input side, and they go through this, again, magnetic tunnel junction structure, and they affect the large magnet here at the bottom in a particular pattern depending on the pattern of voltages that I apply. And the direction of spin that I get in the very center here depends on that. And this spin direction here in the middle forms with the output pillar another magnetic tunnel junction. And so that means the resistance of this part, number 4, depends on the voltages that I apply at 1, 2, and 3. And then I can simply apply voltage between, say, ground here and number 4 and read out that resistance. So I'm applying voltages and reading out another voltage. And so this is essentially a spin gate, but then again interfacing with the outside world via voltages. Finally, here's the last one that I will do. This is called domain wall logic, and I'm applying currents through fixed ferromagnets here at the ends. And let's say I apply a current in here, and I leave the other one alone. Then these currents will be spin polarized by going through the ferromagnet, and they'll inject spins into this conducting channel and actually push this domain wall to the side. And in the center here we have another magnetic tunnel junction structure. And so by pushing this domain wall, I can change again the resistance of this whole stack. And then if I apply another current through it here, then the voltage that I end up with will depend on the resistance. And so this is just like the spin torque majority gate, but instead we're using currents. And we have only 2 inputs instead of the 3. So, finally, what are some of the challenges that we face currently in spin logic and magnetic logic? Well, as I motivated, the total power dissipation is theoretically kT times log R. But we are currently nowhere near that. There's many things that are standing in the way of that, one of which is the amount of energy it takes to switch a magnet, because we are trying to flow charge through some kind of material, and the interactions in that material, say the spin Hall effect metal, convert that charge into current. And that process is currently one of the most efficient ways, but it's still nowhere near ideal. Also, the switching speed of magnets is generally at most as good as state-of-the-art CMOS. In addition, all of these spin logic devices that I've shown that use voltage and current in some way, well, they are indeed moving charge, and so they also suffer the same problems as CMOS, and that is Joule heating, ohmic dissipation, and leakage. Finally, in magnetic logic, we don't have those, but what we do have is a fairly limited speed of the interconnect, because we're chaining together either many buffers and inverters, each of which are limited by this speed, or we are trying to move domain walls, which are intrinsically fairly slow. In addition, some of the experiments that we have performed here at Berkeley have found the reliability of nanomagnetic logic to be fairly poor. And so these are the challenges going forward that need to be solved before we can have viable spin logic.